All right, one last thing we're going to look at is how to simplify what are called complex fractions. Simplifying complex fractions. All right, I'm having to do a whole lot of this in my trig class right now, so I'm glad you're going to be exposed to the skill in case you have to take trig, because I have to use this all the time in there. Okay, so that's the first one we're going to look at, and then there's another one. And let me get you to look at how to handle this. All right, so there's really two methods that you can use on this. There's one that I really want you to learn how to do, but I'm going to show you both methods on number 12 because both of them really work well. Okay, so one method you use just involves rewriting this. That fraction, big fraction bar, is really like a division symbol. So we have 4 over y divided by 6 over y plus 6, okay? And so we just did problems like that earlier on this worksheet. So it's a really nice method for this particular problem. It works great. You would just keep, change, and flip. Okay, remember that y plus 6. That they're together. You can't separate the y from the 6. So now this is just like one big fat fraction. I'm looking for things that are common. Can't knock out the y's because that's addition right there. But I can divide here by 2 and here by 2. And so my final answer will be 2 times the y plus 6. And then in the denominator, I have a 3 times a y. Okay, so that's actually it. You can, sometimes you'll see them go ahead and distribute, but it's okay to leave it in what they call factored form. I like it in factored form because I can tell whether there's any more that I need to cancel out. Okay. All right, now here's the other method. Okay. You have 4 over y, remember, and then 6 over y plus 6. The other method takes advantage of the least common denominator, okay? So what you do is you look at the little fractions and you look at their denominators like we've been doing for the equations and when we were adding or subtracting, and you go ahead and you find the LCD, okay? So in this case, I would need both a y and a y plus 6, okay? And then because we have this fraction right here, what I can do is I can multiply down here by y times y plus 6 as long as I multiply up here by y times y plus 6. Okay? Because see how that really isn't, that's just multiplying by 1. So I'm really not changing it. I'm just changing its name. Okay? So I can do to a complex fraction something similar to what I can do when I have an equation, because there's a mathematical way to handle this where I'm not really changing the original problem. I'm just multiplying the top and the bottom by the LCD. Here's why I would want to do that. This is really understood to be kind of up high where the 4 is. This is really understood to be up high. Let me get rid of that for a second. Up high where get rid of that. Okay. Up high where the 6 is. And so if you now think about the numerator denominator individually, so think about this as one big fraction. There's a y down here and a y up here. There's a y plus 6 and a y plus 6 there. So I wind up having a 4 and a y plus 6 left up on top. And in the denominator, I have a 6 and a y left. Okay. And then the 4 is divisible by 2, and so is the 6. So my final answer is 2 times y plus 6 over 3y. Now, you could easily argue that you like the other way better, and I get that. It's not as convenient, though, in some cases. So this method right here turns out to be an excellent way to handle complex fractions when you have lots of fractions. And that's what happens a lot in trig. Okay, and that's what happens on number 13. And I want you to see how nice the second method works on number 13. So see, number 13 has a 4 plus a 2 over x. Then it has an x over 3 plus a 1 over 6. Okay? So it's got a lot of fractions. And if you wanted to use the first method on this one, you would have to add these two together so that you only had one fraction on top, and then add these two together so you only have one fraction on the bottom. And adding fractions is the worst. That's the most time-consuming operation you do with fractions. So why do that? That's horrible. So the other method, the second method I showed you, works really good in this case. You see how there's a little fraction here, a little fraction here, and a little fraction there. We've got an x, a 3, and a 6. Okay? So the LCD is going to be an x, and really I can just do a 6x because I'm thinking about what I'm going to do with that LCD, right? I'm going to use it to knock out or clear these fractions. And since I would need an x to make that go away, I'd need a 6 to make this go away, I'd need a 3 to make that go away, but 6 would also work here. So you want the smallest thing that would work to cancel out everything. 3 would not be big enough. It wouldn't cancel out the 6. So this will be our LCD. So with that second method, what we did is we multiplied both the top and the bottom by that LCD. So I'm going to do that. I'm going to multiply here by 6x, and I'll multiply here by 6x. Okay. All right. But when you do that 6x, this LCD has to get distributed to both terms, top and bottom. Okay. All right, so we had the 4, but then we needed to multiply it by 6x. We had the 2 over x, but we have to multiply it by 6x. Okay. Then down here, we had the x over 3. We're going to multiply it by 6x. And then we had the 1 over 6 being multiplied by 6x. Okay. So this is a plus, and this is a plus. That's what those were, okay? All right, so now what happens is I look at how here I have an x that's in the denominator, and here I have an x that's on the top. Here I have a 6 and a 6 that's not in the denominator. Those would be 1. 6 over 6 would be 1. Here's an x. Here's a 3 on the bottom. It would go into the 6 twice, so I can knock it out. All right, now what you got left then is you got these 4 spots that are now going to be free of fractions. You got to be careful. 4 times 6x would be 24x. 2 times 6, that would be 12. Here the 6 is canceled. I have a 1 times x, which is x. This is the hardest of all. Okay, this is an x times an x times a 2. So that would be a 2, x times x would be x squared. Okay, so let me make sure that was clear. See, that was x over 3, and when I multiplied by 6 over x, the 3 went into the 6 twice. But then I had a 2, an x, and an x left. That's where the 2x squared came from. And then I had a plus here. All right, so that second method winds up clearing the fractions so that you wind up having just a rational expression that you need to simplify. So you do need to try to factor to see if there's a common factor you can cancel out. So when you pull out the 12, you have 2x plus 1 left. Down here, when you pull out the x, you have 2x plus 1 left. The 2x plus 1s are going to cancel. They'd be equal to 1. So this one winds up being 12 over x. And don't think that you could cancel out the 24x and the 2x squared to get 12 over x. That's just a coincidence. Okay, so that's your final answer. Okay, all right, so that's how you handle complex fractions. I would recommend, if you're only going to use one method, that you use the second method, because otherwise this problem right here, you would not want to have to add these fractions, getting common denominators, etc. Okay, I wouldn't want to have to add these. So the second method, if you're only going to learn one, works in all cases. All right, now let me get you to compare the 3 things. because what's hard is the different way in which you use the least common denominator. So let me go ahead and do kind of an overview of that. So when you're adding or subtracting, you might have something like this going on. Okay. Then if you had a complex number, you might have a fraction divided by a fraction. Okay. And so that's a complex fraction. Okay, or you might have a problem where you've got like an equation. Maybe you have something like 2r equals 5 over r minus 9, something like that. Okay. All right, and that's a rational equation. And you're trying to solve it. Okay, so the first two, this is an equation. The first two are expressions. So this is a rational expression where you're adding or subtracting. This is a complex fraction. Both of these you would just be really simplifying. Here you'd really be simplifying. But here you've got an equation, so the directions would probably say to solve. Okay, so let's look at the difference in how you use the LCD, and then maybe you'll have enough to be able to try to work through some homeworks. All right, so for all of these three problems, the LCD would be the same thing. Okay, so the LCD for all of them, I'm going to move this up a little bit so I have a little more room. Okay, so the LCD for all the problems below this would be the R and the R minus 9. You'd need both of those. All right, so let's look at the different way in which you use them. For this type, okay, when you're adding or subtracting, for this example, you would use the LCD to rewrite each fraction so it had that common denominator. Okay. And so since you already had the R, you need an R minus 9, you're going to come up here and multiply by R minus 9 on the top and bottom. Okay. Over here, you have the R minus 9. You need to multiply by the R, top and bottom. Okay. And so that means you're going to have 2R minus 18 here. Here you're going to have 5R, and now you've got it written so they both have that same denominator. So with adding and subtracting, you can't just knock the fractions, the denominators out of there. You can't get rid of the fractions. You need a common denominator. You'll rewrite each fraction so it has that denominator, and then you just add or subtract the numerators. And then if you can simplify, you do. But you still have the denominator. It's not gone. Okay. The other two, there's a way to clear the fractions, because this one has a big fraction and because this one has an equal sign. So you still use that same LCD, but you use it in a very different way. So here you would multiply by R times R minus 9, top and bottom. Okay. And that makes this one big fraction, and the denominators are going to wind up canceling out. So like here, the R would cancel, and I'd have the 2 times the R minus 9 left on top. Down here, see how the R minus 9 right here would knock this R minus 9 out, and I'd have a 5R on the bottom. Okay, and I can't simplify that anymore, so it would be okay to leave your answer that way or to leave your answer multiplied out. Okay, either one of those is okay. All right, so with this one, there's a way to clear the fractions because you have that large fraction bar and you can multiply by something equal to 1 and it just knocks out those denominators. All right, you can do something similar on this. What I can do is multiply both sides by R times R minus 9. Usually I just write it like this because that's the hardest part of these problems. It's just they can be so much to write that you get overwhelmed. Okay, so if I multiply the left side by R times R minus 9, the R cancels. And I'm going to get a 2 times an R minus 9 left. On the right-hand side, the r minus 9 and the r minus 9 cancels, and I see a 5r over there. Okay, so I was able to clear the fractions, and now I'm just going to come in here and distribute and think about what it is I'm trying to do. This does not have a squared. This is not a quadratic equation. It's linear. So that means I'm just trying to get my variables to one side, my numbers to the other. Okay. So it'll seem a little strange, but the best thing to do next would be to subtract 2r. Since there's no number over here, just moving your variables to the right is okay. Okay, so that would be negative 18 equals 3r. And then I need the r by itself. Oops, by itself. So I'm going to divide by 3. And I'm going to have r equals negative 6. All right, so I anticipate on that one that last part might bug you a little bit. I know I have a lot of people that wind up doing things like subtracting the 5r. Okay, and if you did that, it's okay. You just can't lose track of what you got. You'd have negative 3r minus 18, but it would be equal to 0, and don't lose the equal part. Then you could add the 18, and you'll see you'll get the same thing as I did. Then divide by negative 3, we get that r equals negative 6. But that's old stuff. That's back to, solving linear equations. So you guys are probably okay with what I did right here. All right, and then that r equal negative 6. That negative 6 doesn't cause either denominator to be 0, so it should be okay. All right, so that's your end result on that one. Either one of these is okay here, and this is your end result there. Okay, so I just wanted you to have one situation, because what's confusing is they feel like they're similar. Okay, they are similar. Whether you're adding or subtracting, dealing with a complex fraction or dealing with a rational equation, a lot of times we're using the LCD, the r times r minus 9. It's just we use it in very different ways. And the big thing that people try to do that they can't is you can't clear the fractions when you're adding or subtracting. You can't knock them out. Where here you could knock out the little fractions. Okay, and you could knock out the little fractions there. Okay. All right. So I'm going to stop that video, and that all I've done so far is just worked out the more on rationals, done several different videos on that. That's going to be something where you're going to want to take good notes and then work through the homework very carefully. Don't use those apps and shortcut it. Really work to understand it as best you can before you try the test on it.